children, my goal today is to help you understand surface tension. Myself, Dr. DIGNA VARGHESE. Surface tension is an effect where the surface of a liquid is strong. Surface tension is the tendency of liquid surfaces to shrink into the minimum surface area possible. In other words, the surface can hold up a weight. In material science, surface tension is used for either surface stress or surface free energy. Therefore, surface tension can be defined as surface tension is a property related to intermolecular attractive forces within a liquid. Please listen, children. Surface tension is a property related to intermolecular attractive forces within a liquid. You are very familiar with some examples of surface tension. Small insects such as water strider can walk on water because their weight is not enough to penetrate on the surface. A carefully placed small needle or a paper clip can be made to float on the surface of water even though it is several times as denser as water. Water dripping from a tap, just like a drops. Tears of wine is the formation of drops and rivulets on the side of a glass containing alcoholic beverage. Bubbles are round or in spherical shape. The surface of a water droplet holds the droplet together in a ball shape. After these examples, now we will discuss surface tension in detail. In a liquid sample, intermolecular forces exert different effects on a molecule at the surface and on one in the interior. From the picture shown here, in a liquid sample, we know there are so many molecules are present. Here we are representing only two molecules. One is the molecule situated in the interior and the one is the molecule at the surface. The molecule situated in the interior attracted by other molecules which are surrounded by the molecules given here. That is, it is equally attracted by other molecules from all sides in the bulk. So this particular molecule feels no resultant attractive force. Okay, but this is not the case for the molecules situated at the surface. These molecules are attracted by the bulk molecules, that is pulling this molecule, surface molecule, to the bulk by the molecules situated in the interior. Okay, and also by the molecule present the sides of the surface molecule. But there is no molecules present above the surface molecule. In the liquid state, there are only gaseous molecules are present, or the molecules present in the vapor phase that are not liquid molecules. So there is an unbalancing or a non-uniform distribution of attractive force. Okay, that means the molecule at the surface feels at the attraction of the bulk only. Of the bulk of the other molecules, that is an inward pull from the molecules present in the bulk. So the molecule at the surface always feels a resultant inward pull from the molecules in the bulk of the liquid. Due to the resultant inward pull felt by the molecules at the surface, the molecules present at the surface, there is only inward pull by the interior molecules present in the bulk of a liquid. The molecule at the surface behaves as a state of tension, or it behaves as if it were in a state of tension, like a stretched elastic film or membrane. This property, what we call it as a surface tension. Once again I will tell you, children, the molecules present at the surface of a liquid feels the attraction of the bulk of the other molecules which are present in the interior. That is, it feels a resultant inward pull from the molecules in the bulk of the liquid. The resultant inward pull felt by the molecules present at the surface. A liquid surface behaves always as if it were in a state of tension. This property, what we call it as a surface tension. Hope you understand what is surface tension. We can now define surface tension in another way. Surface tension. Surface tension is the force acting at right angles to any line of unit length along the surface of the liquid. Consider an imaginary line on the surface. Both the sides of surface there are molecules, and these molecules exerts a force which is right angles to the line. This force, these molecules near the line exerts a force. This force acting on the line is equally, so there is a stretching, and this stretching is also occur by the equal force exerted right angles by the molecules near the line. This pull or tension of a liquid is known as surface tension. Remember, surface tension is not a force, but it is a property of a liquid. Now we can say that force is proportional to length. Okay. For unit length, that particular molecules acting or exerts some force right angles to this particular line. So F is equal to surface tension into length. That is, surface tension is equal to force by length. Surface tension denoted by the letter gamma, and its unit is Newton per meter in SI system. In CJ system, dynes per centimeter. The effect of surface tension is to reduce the surface area to a minimum. So if we wish to increase the surface area, from this to this any value, we have to do some work against the force of surface tension. Remember, surface tension is a property which is always have a tendency to reduce the surface area to a minimum value. But if we wish to increase the surface area, we have to apply some work against the force of surface tension. Obviously, that process requires expenditure of energy. Okay, the work or energy required to increase the surface area of a liquid by 1 unit is called surface energy. Okay, in other way we can say like that the total energy per unit area of the surface is called the surface energy. Its unit is joule per meter square in SI system and in CJ system ergs per centimeter square. Surface tension is a property of a liquid. Surface tension is a property related to the intermolecular forces in the liquid. Here we can see from this table surface tension of some liquids at 298 Kelvin. The liquid is water. Its surface tension is 7.275 into 10 raised to minus 2 at 298 Kelvin. The unit is Newton per meter. Ethanol, it is about 2.2 into 10 raised to minus 2. Glycerin 6.52. Mercury 5.2 into 10 raised to minus 2. Carbon disulfide 2.68 into 10 raised to minus 2. Toluene 2.843 into 10 raised to minus 2. Acetone 2.37 into 10 raised to minus 2. Benzene 2.89 into 10 raised to minus 2 and diethyl ether for 1.7 into 10 raised to minus 2. In the case of water, the surface tension is more. And second one is for glycerin. Okay, in this case of water and glycerin, there is a strong intermolecular force of attraction that we called hydrogen bond. Okay, hydrogen bond is a bond formed between the most electronegative element and the hydrogen atom. In the case of water and glycerin, there is oxygen. So that is attached to the neighboring molecules hydrogen, okay, and forming hydrogen bond. So in the case of water and glycerin, there is hydrogen bond and so the value is high. Greater the intermolecular forces, the greater of the surface energy or surface tension. Surface energy is nothing but surface energy. The surface can hold up a weight. A metal needle or paperclip has higher density than that of water, but we know it can float almost forever. That is due to the surface tension of water. When we dropped a needle into water carefully, otherwise it falls down into the bottom of water. If we put it horizontally on the water with a lot of caution, it can float almost forever. That is due to surface tension. So surface can hold up a weight. This is due to the fact that intermolecular forces create surface tension. The water molecules, there are hydrogen bonding at the surface which are pulled in and also by the cohesive force between themselves and molecules inside the bulk, and thus have higher potential energy here than the bulk of the liquid. Here potential energy is more, here kinetic energy. Okay, so this surface energy or surface tension holds the metal needle floating. Now we are moving to the next topic, some clearly observable consequences of surface tension. First one is the spherical shape of liquid droplets. We know surface tension reduces the surface area to a minimum. For a given volume of a liquid drop tends to assume a spherical shape. Why? For a given volume of a liquid, a sphere has the minimum surface area. If two small drops encounter each other, they tend to coalesce into a larger drop has a smaller surface area than the two small drops. Okay, so surface tension reduces the surface area to a minimum. There is a question arises, a liquid drop tends to assume a spherical shape. That is because of, for a given volume of a liquid, a sphere has the minimum surface area. Capillarity and meniscus formation. When a capillary tube is dipped in a liquid, capillary tube is a tube having small diameter glass tube which is placed upright in water, some or any liquid. There will be a rise occurs, that is known as capillary rise. In some other liquids, if capillary tube is dipped, there will be a fall occurs, that is known as capillary fall. Capillary rise and capillary fall collectively known as capillary action, and which is related to surface tension. Here we explain the capillary rise. Water molecules is taken in a beaker and a capillary tube is dipped into this. The water creep up the wall of the glass capillary. So there is a capillary rise occurs due to surface tension. What will be the reason for the capillary rise? Water molecules happen to be attracted to the glass of the capillary tube due to adhesive force. Adhesive force is that force occurs between different kinds of molecules or different kinds of compounds. Here water and glass is different compounds. Water molecules, within the water molecules there is hydrogen bonding, and we know silicate molecules are in the glass, present in the glass. So in the silicate, that is SiO2, here a strong electronegative element, that is oxygen. In the case of water, the molecular formula is H2O. Here also hydrogen bond form with the neighboring water molecules. After all, we know surface tension is a property of liquid by the intermolecular forces. Okay, and here within the water molecules there is hydrogen bonding, and between different kinds of molecules, that is one is glass molecule and the other is water molecules, here also some kind of hydrogen bonding. This is known as, in a general case, adhesive force or adhesive attractive force between the glass and water. Here, in between the water molecules, this is cohesive force. Here, adhesive force is greater than cohesive force. That is, adhesive force between water and glass is stronger than the cohesive force between the water molecules. So, a thin film of water creeps up the wall of the glass capillary. Okay, there is forming a capillary rise due to adhesive force between the water and the glass, which is more stronger than the cohesive force within the water molecules. And there is a meniscus is formed, or a liquid surface within the tube has its middle curved downward and edges curved upward. Middle curved downward and edges curved upward. That is, it has a concave shape. So it is known as concave meniscus. The final water level is a balance. Here a balance occurs between the surface tension and the potential energy. Okay. So here capillary rise occurs, and this is due to the adhesive force between water and the glass molecules more than the cohesive force between the water molecules. Here the liquids wet the glass, that is, capillary rise is observed. Here an angle theta, that is the angle and the curved surface or the meniscus with the wall of the tube. That angle is known as angle of contact or contact angle, that is represented by theta. Contact angle is found by drawing a tangent at that point. The angle which curved the angle within the curved surface. Here we know the angle within the curved surface, which the curved surface, that is meniscus, makes the wall of the tube. Here wall of the tube, and there is a tangent drawn at that point, and this angle is known as what we call as angle of contact. For capillary rise shown by wetting liquids, theta is always less than 90 degree. Now we are discussing the capillary fall. Here we are taking mercury here, and a capillary tube is dipped to the solution. Mercury. In mercury there is strong metallic bonding, that is a cohesive force, and there is adhesive force between mercury and the glass tube. There is two forces acting. One is cohesive force within the mercury atoms, and other one is adhesive force between the mercury and the glass. Here the cohesive force is more stronger than the adhesive force. So there is a mercury glass tube is placed in a beaker or containing mercury. The mercury level in the tube drops below that in the dish. Okay, you can see this, the level of mercury in the beaker and also the level of mercury in capillary tube. That is, the level is smaller than the dish. So it is a capillary fall or capillary depression. Here observes a capillary fall or a capillary depression. Also the meniscus in the middle is curved upward and edges curved downward. So it has a convex meniscus. This behavior of mercury results from the fact that the attraction of cohesive force between the mercury atoms is greater than the attraction between the mercury atoms and for glass, that is adhesive forces. That is just opposite in the case of water and glass. Here a angle, that is a tangent drawn at the meniscus and also the wall of the capillary tube, that is represented as theta, that is the contact angle or angle of contact. For a capillary fall, the angle is always greater than 90 degree, that is theta is greater than 90 degree. So the liquids do not wet glass. Okay, if contact angle is less than 90 degree, the liquid is wet the surface. If contact angle is greater than 90 degree, the liquid do not wet the surface. So for liquids that wet glass, the capillary rise is observed. For capillary rise shown by wetting liquids, theta will be less than 90 degree. For liquids that do not wet glass, capillary fall is observed. For capillary fall shown by liquids that do not wet glass, the contact angle is greater than 90 degree. Water spreads on glass while mercury as a drop. We know some liquids wet a solid surface but some do not. We know a familiar experience that water wets glass while mercury does not wet glass. The difference can be explained in terms of surface energy. Surface energy is nothing but that is surface tension. And consider a liquid L. Consider a liquid L resting on the surface of a solid S and comes into contact to the equilibrium. Let the angle of contact is theta. GS, LS and GL represent the GS represents the gas solid interface, LS represents the liquid solid interface, GL represents the gas liquid interface, and theta is the angle of contact. And gamma represents the surface energy that is acting here. At equilibrium, the forces acting at the interfaces must balance. Okay, if gamma is the surface tension of the liquid, then gamma GS is equal to gamma LS plus gamma GL cos theta. That will be the conditions at equilibrium. The angle of contact theta, which depends upon the value of surface tension at GS, surface tension at LS, surface tension at GL, etc. The angle of contact theta depends on the values of gamma GS and gamma LS. If gamma GS is greater than gamma LS, cos theta is positive, that is theta is less than 90 degree. If gamma GS is less than gamma LS, cos theta will be negative and theta is greater than 90. We know if theta is greater than 90 degree, that means the solution, the liquid do not wet surface. If gamma is less than 90 degree, the liquid wet surface. Okay. In the case of water, glass interface, here theta is less than 90 degree. So water spreads on glass. In the case of mercury, that is theta is greater than 90 degree. So mercury do not wet the glass and mercury remains as a drop while water spreads on the glass. Okay. Effect of temperature on surface tension. We know kinetic energy is a function of temperature. If temperature increases, kinetic energy of the molecule increases and thereby a tendency to break the intermolecular force of attraction. So, intermolecular force of attraction decreases. Therefore, the surface tension decreases as the temperature is raised. But this is not always the same. There are some exceptions for the liquids. That is, liquid crystals, some metals like cadmium, iron, copper. In that case, surface tension decreases as the temperature decreases. Surface tension increases as the temperature increases. So, there is some exceptions. Okay. But most of the case, as the temperature increases, surface tension decreases. There is a well-known equation called Ramsay-Shield equation. Gamma m by rho raised to 2 by 3 is equal to k into Tc minus T minus 6, where gamma is a surface tension or surface energy and m is the molecular mass, rho is the density. K is a constant at a particular temperature T Kelvin and Tc is the critical temperature, T is the temperature in Kelvin and 6 is a constant. But in this equation there is a discrepancy. When gamma is equal to become 0, it is not when T is equal to Tc, but when T is equal to Tc minus 6. Okay. So, in order to overcome this discrepancy, Katayama modified an equation, that is gamma m by rho minus rho dash is equal to k dash Tc minus T. You can see from this table there is some variation of surface tension with water at different temperature. Here water at 0 degrees Celsius, its value is 7.57 into 10 raised to minus 2. Value is 15, its value decreases. As the temperature increases, kinetic energy of the molecule increases and thereby intermolecular force of attraction decreases. So surface tension also decreases. 15 degree 7.35 is value, at 20 7.275 value, at 25 degrees 7.20, at 50 degrees 6.79. You know at 100 degrees Celsius 5.88 into 10 raised to minus 2 is a surface tension value. So as the temperature increases, surface tension of a liquid decreases. Thank you for watching video.